So this is Newton's third law of motion and its interaction forces. So basically, Newton's third law of motion states that whenever an object exerts a force on a second object, that second object exerts an equal but opposite force on the back onto the first object. So when we're talking about how forces will cancel out, it's basically saying that the forces, when acting on the same object, will cause the force to cancel out, yielding a net force of zero. But Newton's third law does not talk about how the net force becomes zero, because what happens here is that Newton's third law states that it's not so simple. Whenever a force is applied to one object, from object A to object B is going to exert the same force back onto object A. So we have a exertion of force on two separate objects by two separate objects. So the net force in this case is not going to be equal to zero. Now, Newton's third law states that to every action there is always an equal but opposite reaction. So that kind of goes in a way of being a kind of a simpler way to explain it, but it actually gets a little bit more complicated than that. So with regards to your review, you may want to listen to that last 45 seconds over again, just to make sure that you can sort of hear the differences in the terms that are being used. Okay, so whenever we apply a force onto something, we call that an action force. So if I'm exerting a force onto the chair of 10 newtons, then my action force is 10 newtons on the chair. And the reaction force is basically the force exerted by the chair onto me. So if you notice, I'm exerting a force on the chair, so the force is displaced on the chair. But the chair will exert a force back onto me. So that exertion of force are two separate objects, even though the magnitude is the same, 10 newtons, but the forces are exerted on two different things, me and the chair. So in this case, here the example is the action-reaction pair with regards to the balloon. So if you blow a balloon and you let it go, and we'll be doing this on Wednesday, the air rushes out of the balloon. And so that's the action force, air rushing out. And the reaction force is that the balloon is pushed upwards in this example. So here I have the situation where a person is pulling on a rope, as seen on the top picture, and the scale reading is 500 newtons, and the rope is connected to a wall. If the person is exerting a force, an action force, on the wall, he's exerting 500 newtons of force, then the wall is pulling back on him with 500 newtons of force. The scale will still read 500 newtons because it's not the number of forces that are acting on the same object. It's the force that's acting on separate objects. This is akin to the same scenario as the bottom one, where a person's pulling this way of 500 newtons of force and the strongman is pulling in the opposite direction at 500 newtons. It's the same thing because for every action there's an equal but opposite reaction. The forces are displaced on different objects. So when we look at action-reaction forces, we're looking at forces in pairs. And the interaction of forces will always occur as pairs. And because it occurs as pairs, we are going to look at the action force, the reaction force. That is the forces in pairs. So when you are walking, you're pushing back on the ground. So you're pushing backwards on the ground, you are exerting a force on the ground. Then the ground will push back on you. So when it forces the reaction force, and that pushes back on your feet, causing you to move forward. Okay, so think about how you move, and then we can relate that to actual motion. So the action-reaction force pairs is where the action force is when object A exerts a force onto object B. If you notice, the force is exerted on B, not on A. And the reaction force is object B will exert a force back onto object A. So if you notice this, the example is the forces are on object A and the other forces on object B. They're not on the same object. If they were on the same object and they were equal and opposite, then you have a net force of zero. But in this case, it is not true. Person A will push on object B. Person A pushes on person B. So here's A and here's B. And when they pushes on each other, the reaction force, and what is the reaction force? So you can kind of go with a formula up on top and be able to answer those two questions. So let's go back to Newton's third law. I'll call myself object A, exerts a force on a wall, which is object B. Then the wall will exert a force back onto me. Okay? So object A, me, I'll exert a force on object B, which is the wall. So the force is on the wall. And as the reaction, the force that the wall will exert back onto me is equal, but opposite in direction. So if I exert 100 newtons of force onto the wall will exert 100 newtons of force on me. So if I'm very angry and I punch a wall, the reaction force is back on my hand, which is pretty painful. So now net forces, again, revisited. When we talk about net forces, we talk about how forces can be at equilibrium, where two forces are acting on opposite direction are exerted on the same object. When the forces are exerted on the same object and the forces are equal, the net force will then equal to 0. However, in the idea of Newton's third law, the forces are not acting on the same object. It's not acting on the one object. It's acting on separate objects. So the forces cannot cancel each other out as in terms of the net forces. So here I have air resistance. I have in terms of the skater here, the skater will then push on the skateboard, and the skateboard will then be basically have pushed forward, causing the skateboard to move. The skateboard move forward, let's just say with 100 newtons of force. The air resistance will be acting on the skater's push, so then we have opposite action of 100 newtons of force. Therefore, you have the situation where the net forces are canceled. But in terms of Newton's third law, that's not true. Okay, and if you have any questions on that last slide, please feel free to answer it, and so you are able to, get your questions and concerns answered. Now over here there are 6 pairs of action-reaction pairs. You may want to identify them. We'll get to this in class, but try to have some answers written down so we can have some way of, a discussion in class. So go ahead and pause and write down the 6 pairs of action-reaction forces. Okay. So the effects of action-reaction pair is done by means of the calculation force is equal to mass times acceleration. So there is an interaction between a stone and the earth as the stone falls towards the earth. Is there a force acting on the stone? And of course, if you had said yes, it's gravity. And because all things are action-reaction force pairs, then there has to be 2 forces, one acting on the rock, the other one acting on the earth. So then now the question remains, which of those 2 forces are greater? Please explain. And so now you have to decide what is the acceleration of the stone. Suppose that the mass of the stone is 10 kilograms. If you don't know how to answer this question, you may want to consider reviewing F equals ma, because the equation is right below. So now, what is the acceleration of the Earth? In this case, if the mass of the Earth is 6.0 times 10 to the 24th kilograms. We're going to be doing this in class a little bit this week, but I just want to get through part of the slide first so that we can at least get some of the concepts down. So the concepts are better explained with a little bit of math. But the Newton's third law of motion, the interaction force problems, they're not going to be introduced till next week, and I will introduce that probably Thursday or the latest Friday. So using this, go ahead and calculate for the acceleration of Earth. Again, we'll be doing this in class, but try to have some stuff down on paper so that we can have some forms of discussion. So here I have a stone, and it's falling towards the Earth, and because the Earth exerts a force on the stone is going to accelerate downwards. But at the same token, since there's an action-reaction pair, the stone is also going to be exerting the same amount of force on the Earth, pulling it upwards towards itself. But if you notice, the arrows are on separate objects. The force of the Earth on the stone is acting on the stone. The force of the stone on the Earth is acting on the Earth. So then you have 2 different forces that are acting on the same object. One thing about this diagram is incorrect is that these 2 arrows should be the same length because the forces should be equal. Now, because the forces are equal, and Earth has a huge mass, and stone has a tiny mass by comparison, what do you think will happen to the acceleration? Because according to the third law, it's equal but opposite forces. Equal forces, opposite in direction, but those forces, the action force and the reaction force, are acting on different objects. And so then what will happen is that the force will cause a change in the object's acceleration, because force and mass are inversely proportional. So what happens now, since the stone has a tiny mass, it will have a greater acceleration towards Earth. And what is the acceleration of a stone towards the Earth? Approximately 9.80 meters per second squared towards Earth. And so how would you calculate the acceleration of Earth towards the stone? Well, since Earth has such a huge mass, it's very difficult for us to detect the acceleration of the Earth towards the stone. So here's what it looks like. Since the force of the Earth on the stone is going to be equal to the force of the stone pulling on the Earth, and since the stone's mass is so small compared to the mass of the Earth, the acceleration of the stone is going to be huge comparing to the acceleration of the Earth towards the stone. So we can go ahead and calculate for that, so we can see how that actually works and why it's virtually undetectable. And we'll be doing that in class. So if you were jumping out of an airplane when attempting to skydive, the ground actually moves up towards you a tiny bit to meet up with you. I kind of like this picture. It's pretty funny. So take a moment and celebrate this picture. So now, let's talk a little bit more about action-reaction pairs. So now that we can go through this, we can actually start talking about why bullets are so fast. Now, the gunpowder in a bullet casing will ignite and will cause an explosion. And that explosion will exert a force on the gun and you, right? Because you're holding onto the gun, presumably. And that's the action force. And since the gun and you are one and the same, pretty much because you're holding onto the gun, it will exert the same amount of force back onto the bullet, but it'll be in the opposite direction. So you see the force is acting on you, and then the reaction is the force acting on the bullet. And so that's the opposite direction. And since Newton's second law states F equals ma, mass acceleration inversely proportional, we can say that the acceleration is huge because the mass of the bullet is so small, and the mass of you and the gun is so much bigger, therefore the acceleration is pretty small since the forces are the same. So right now we're just going to stop here for part 1. Part 2 is a little bit more conceptual stuff. It is in my opinion that you might want to look through the PowerPoint so you can get a heads up, since this week's quiz is based on the conceptual stuff, and this whole PowerPoint and this screencast, part 1 and part 2, is essentially all conceptual. So, but I'm going to stop here for now, since each screencast should not be any longer than 15 minutes. Therefore, it's going to stay at this point. Okay, be ready to do the web assignment. I'll see you tomorrow.